Let's talk about graphing rational functions. Rational functions are also known as fractional functions. So they're places on your graph that will be undefined. We call these places asymptotes, and they're invisible lines in space that a graph gets closer and closer to but will never touch because your function is undefined at that value. For vertical asymptotes, so these are imaginary vertical lines, we can set the denominators of our function equal to 0 and solve to figure out the values that would make it undefined. Horizontal asymptotes, you have to compare your numerator and your denominator. So you want to make sure that the numerator and denominator are in standard form. So that means you have your largest degree term in the front. And then we could look at the degrees and compare them. So if the degree in your numerator is less than the degree in the denominator, so we could say in generic terms here, if n is less than m, then your horizontal asymptote is automatically y equals 0, which is the x-axis. That's the most common type you will see. If the degrees are equal, so in generic terms, if n equals m, you will put the a over the b value, and your horizontal asymptote will be equal to y equals whatever the numbers are for that example. A lot of times that would equal 1, because you may not have actual numbers other than 1 in the leading coefficient place. But we'll look at some examples. If n is greater than m, so if your degree in your numerator is larger than the degree in the denominator, we have no horizontal asymptote. So let's look at how to find just our asymptotes first before we get to sketching our graphs. So for these examples, we're just going to work on finding those asymptotes, because that's the most important part when you go to sketch your graph, is that you sketch these first. So for our first example, we have the function x over x squared minus 1. So to figure out our vertical asymptote, we would need to set the denominator equal to 0. So x squared minus 1 equals 0. We can use our factoring skills to factor that as a difference of squares, and we would end up with x would be equal to -1 and x would be equal to +1 would be our vertical asymptotes for that function. Now let's look at horizontal. So for our horizontal asymptotes, we compare the degrees in the numerator and the denominator. So here our degree is smaller in the numerator than it is in the denominator. That's the most popular type you see, because that's typically what happens on a rational function. The denominator usually is larger. So we would just say y equals 0, which is also the x-axis. Let's look at example 2. So for the vertical asymptote, again here, we're going to set the denominator equal to 0 and solve. So sometimes you might have a simple denominator like x plus 1. So when you set it equal to 0, you could subtract 1, and you would get x equals -1 as one vertical asymptote. So notice some functions have more than one vertical asymptote. Some might have one, but that's okay. Let's look at the horizontal one. So for horizontal, again, we compare the degree in the numerator and the denominator. So these technically have a degree of 1, so they have the same degree. So when that occurs, we would say y equals a over b, and from our example, a is the leading coefficient in the numerator and b is the leading coefficient in the denominator, which in this case is a 1. So we would say that's equal to 5 over 1. So y equals 5 would be our horizontal asymptote for that graph. Let's check out example 3. I have x squared minus 1 over x minus 1. So for the vertical asymptote, we still set the denominator equal to 0. So we quickly get that x would be equal to 1. So it has one vertical asymptote at x equals 1. And for the horizontal, we would compare the degree in the numerator with the degree in the denominator. So here, if the degree in the numerator is larger than the degree in the denominator, we say there's no horizontal asymptote for those. So let's look at some examples of how to sketch our graph. Okay. So looking at example 1, let's first find the vertical and the horizontal asymptotes like we did on the last few examples, and then we'll sketch the graph. So for the vertical asymptote, set the denominator equal to 0. So if x plus 1 equals 0, our vertical asymptote will be at x equals -1. For the horizontal asymptote, we look at the degrees. So the degree in the denominator is larger. So my horizontal asymptote will be at y equals 0. So let's sketch our graph. So a good sketch would be to put our asymptotes on the graph first. So go to x equals -1 and draw a dashed vertical line. And it's good to label that that's a value of -1, and I'll show you why in just a second. And then y equals 0, or the x-axis, a lot of times when we sketch, we kind of put it right on the axis, but so we can tell that there's an asymptote right there. And then if we were not allowed to use our calculator, we could make a table of values. If you're allowed to use your calculator, you would need to make sure that you put this denominator in parentheses when you type that in y equals, so it would treat it properly. And you would tell your calculator -5 divided by x plus 1 grouped together, because if you don't type it that way, you would get the wrong graph. But let's say we're not allowed to use our calculator. We could test values. So I need to know where my graph is going to go if it were less than -1. What would happen over here? So less than -1 would be -2. So if we plug that in, we get -5 over -2 plus 1, which is -5 over -1, which is +5. So I have the point -2, +5. So if that's part of my graph, on these graphs of rational functions, as you'll see on your calculator, you get these little branches, is what we call them. They look kind of like a boomerang, but if I know my graph is going to be at -2, 5, I know it would have to be up there where the numbers would be positive, and it's -2, +5. Now let's try another value that would be over here to the right of -1, or larger than -1, so let's say maybe 0. So -5 divided by 0 plus 1, which is 1. So that's just equal to -5. So I have the point 0, -5. So at 0, if it's negative, my graph would also be down here in this area. And again, it would look like a little branch. It approaches your asymptotes, but it would never touch them. It looks like it gets infinitely close to those imaginary lines, but it technically will never touch them, because at that point, your graph is undefined. At that point, your denominator would equal 0, for instance. So let's look at example 2, x minus 1 over x minus 3. So to find the vertical asymptote, you set your denominator equal to 0. So we get x equals 3 is going to be the vertical. The horizontal asymptote, we just compare what's happening in the numerator and denominator. So our degree is the same. They're both equal to 1. A is 1 and B is 1. So in this case, we get y equals 1 over 1 or 1. So it reduces, and we can sketch our graph. So draw a coordinate plane. We can put x equals 3 is going to be our imaginary vertical asymptote. And again, it's a sketch. So you want to label that that was 3. So someone looking at your graph would have a good idea of what's going on. And at y equals 1, we need to sketch a horizontal imaginary line that my graph will get close to but never touch. So we can put a little 1 right there. And now, like I say, you can type this in your calculator if you're allowed to use your calculator. Just make sure that x minus 1 and x minus 3 would be in parentheses when you type it in y equals. If you're not allowed to use your calculator, we can always just pick some values and test them out and see where our graph will end up. So 3, a number that's less than 3 that would be easy to check would be something like 1. So what if we plugged in 1? 1 minus 1 would be 0. 0 divided by anything, which in this case would be -2, is still going to be 0. So if I have the point 1, 0 as part of my graph, I would go to 1, 0. So I know my graph would end up right about here. And then again, it looks like a little branch of a graph. You'll see it when you type it in your calculator. A number larger than 3, so we could check 4. 4 minus 1 would give us 3, and 4 minus 3 would give us 1. So then we have the point 4, 3 is part of our graph. So if 4, 3 is part of our graph, we know our graph would have a little branch up here. And if we're just sketching our graph, they don't have to be perfect, but that is a good sketch. We can see where the graph would be approaching, but it would be undefined, and we can tell where the major parts of our graph are going to end up and where they're not going to end up. So let's try one more. If I have f of x equals 2x minus 1 over x plus 5, my vertical asymptote would be where my denominator equals 0. So if x plus 5 equals 0, when x equals negative 5, my denominator would equal 0. So that's the the vertical asymptote. The horizontal will be comparing my degrees. So these degrees are the same again. So in this case, I have a is 2. So when y equals a over b, we'll have 2 over 1, which is just 2. So we can sketch our graph. You want to sketch your vertical asymptote at x equals negative 5. So just need to label that that's what that means. And then y is equal to 2 is the horizontal asymptote. And again, if you were allowed to use your calculator, you could type that in. Just make sure to put these binomials in parentheses so they're treated properly. But if you're not allowed to use your calculator, you could check some values on your graph. So less than negative 5 would be, let's say, negative 6. So let's plug in negative 6. So if I put 2 times negative 6 minus 1 over negative 6 plus 5, I'll end up with negative 6, and then negative 12 minus 1 is negative 13 over negative 1, which gives me negative 6 positive 13. So that tells me my graph would be in this region. And then we could try a number that is greater than negative 5. So we might try 0. 0 is usually a nice easy one to attempt to plug in. So 2 times 0 minus 1 would be negative 1. And 0 plus 5 would be 5. So if it's 0, negative 1/5, that would definitely be in this part of my graph. And again, these graphs are not real accurate, but they give us a great sketch. So we know our graph would be in this area and that area and look like a little branch. They look like they're approaching our asymptotes, but they'll never touch. And then we need to especially know where those asymptotes are, because those are the most important part of these graphs.